on. All right, there's actually one instruction called the one-shot or transitional contact. Is often used to automatically clear or reset a counter. The one-shot can be triggered from a momentary signal or from a signal that comes on and stays on for some time. It will stay on for one scan cycle and then goes off. It stays off until the trigger goes off and then comes on again. So that's a one-shot instruction. Again, this concept of off to on to off transitional contact provides a one-shot pulse when the trigger signal makes a off to on transition. There goes where it goes from false to true. And then the on to off, that's the other way when it goes from true to false. Okay. So there's actually one instruction called one-shot rising, OSR. Is an input instruction that triggers the event to occur one time. Okay, so when LS1 is active, one-shot reset, right? No matter if LS1 stays on, right? It's not going to do anything else. Just fill the trigger and shot one. Up counter with program one-shot rising, OSR, off to one transitional constant instruction. So this is an example. When input 3 comes on, right, then the one-shot instruction will count up. No matter if that stays up, it's not going to count multiple times. Here's the simulated option for the one-shot. Okay, so that's the one-shot instruction. Here's one shot used to freeze rapidly display LED values. Okay, so closing the push button PV0 will freeze and display the value at that point. So you just want a single value to be displayed. All right, alarm monitor program. This actually uses timers, counters, and a one-shot instruction. It's got a float switch, and it's got a multi-position selector, right? And then, of course, again, got a on-delay timer, and up counter. All right, the counterpart of the up counter is the down counter. It's the same idea, right? Will decrease by 1, and usually you can have a kind of a combination counter, which you can do both at the same time. But this is the graphical of the up and down counter. We have 6 shots, right, for the count up, and then we have 4 shots for the count down, and then we have the actual preset value in between, and then the reset. This is what I was mentioning earlier, the parking garage counter program. The sensor at the entrance gate, the sensor at the exit gate, and then the counter itself. And this is set to 150 units. That's the capacity of the parking lot. And so This one doesn't have a digital display, but it has a light indicating whether the parking lot is full or still got, one spot. I have a friend that we used to teach at the 2-year school in Indiana way back, that this year he retired from teaching and went back to industry. And we're having a conversation, and a big part of it, he's a maintenance manager for a Indiana University campus in Indianapolis. And he was just telling me about, one major task that he's got with his team is to maintain the controls in parking lots. So that's a giant application of controllers. All right, so he said we got PLCs all over the place for mostly all of the parking lots at the campus. I don't think we have any of those here. And for semi-rural, small communities, that's not a problem. But when you talk about Indianapolis, that's a 1 million people campus of 25,000 students, right? So you need to control a lot of those parking lots. So this is a big application. Countdown counter instruction. We already mentioned this is very similar to the count up, right? You have an enable beat, you have a down beat, underflow, and then you have to reset the instruction. All right, same as the up counter, right? But they're the same. It's just a function that it does. So here's how it looks in a block format, right? You have the counter name, the preset value, the accumulated value, the counter up, and the down beat. Now remember, there's other hidden bits, right? That you can do stuff with. They're within the counter itself. But these are the most popular bits that are used for useful things. Okay. So the down bit in this case, you want the down bit indicator or the down bit to enable something when you're done with the count. All right, up and down counter is basically combining them both. Do you have the ability to count up and count down? Here's an example. What do you observe on these two counters? What do you observe? If you look clinically at the counter backs, what do you observe? There's something common on those two counters. Apparently, we're talking about two counters, right? But they're not. If you see the counter name is C5 column 2, right? For both, that means you're actually using in memory the same counter, right? You're just setting one. In other words, you're spreading the functions of this counter, and it's exactly the same counter as far as the computer and the software is concerned. But somehow you have the virtuality or blessing to use that same counter to do two things. Okay, so that's and it's a kind of a important detail, because if I were to name this C5-1 and this C5-2, then I'll have to, do the program a little bit different. But that's an advantage. Continuous monitoring of items in processes. The accumulated count of the counter continuously indicates the number of in-process parts. So you have a photoelectric sensor coming in, you have a material processing system, and then the photoelectric sensor. Same idea of the parking lot, right? You want to know how many pieces you put in and how many pieces you got out. So at the end of the shift, you're not going to leave in-process parts that will ruin. So here's the option to set up that counter. Again, it is exactly the same counter, C5-1. C5-1, it's only performing two functions, counting up and counting down. In-feed count, out-feed count. I think we mentioned also the traffic control systems, which nowadays a lot of them use controllers and PLC. And I know there is two flavors in there for the usage of counters. So I think most of the modern traffic control systems have a camera that look at frequency of car circulation, right? And that's how they, shift back and forth. But the early PLC control traffic lights, and there's many of those still, they were based on count. In other words, you'll let 12 cars go come this way. When that count is over, you shift it over to the other side. You let 12 cars go the other way. And so that wasn't actually an early application of counters too, letting a dozen of cars go this way while the other are waiting and so forth. New systems, I think, are they use cameras, right? And they look at the frequency, and I don't know the details, but it's a little bit different. It's not just count. You can cascade counters, depending on what you want to do. If the count available on the controller is not enough, then you need to find a way to interconnect them, right? You can have two counters that will be able to count beyond the maximum count. Okay, so now you're multiplying the gain of your count. There's an example of that. Observe that when this counter counts 10, this one counts 1, right? And that's a way to maximize the count beyond the maximum count for. You have application that estimate large in count, then you want to have a form of a counter feeding another counter. First counter will feed the second counter, and you have a multiplicative effect. So when the two counters count their maximum, you have a count of 27 or 25, I'm sorry, 5 times 5. And that's the same concept for large counts. There you go. I think some of you asked about this idea here, 24-hour clock program. You can actually build your own clock program using, in this case, counters and timers. So you have a retentive timer on. You have a counter up. You have a counter up down here. The first timer counts the second counter counts the minute, third one counts the hour. Therefore, you can build your own PLC-based 24-hour clock. Yeah, we're going to be here for a while if we do this, so I'm going to have to skip it. But that's the idea. Oh, what is going on here? Interesting. I don't know what the issue is. Simulated time for an event program. So again, the idea of the timer, counter, and the 24-hour clock cycle. All right, incremental encoder counter applications. I think we briefly mentioned some of this. And these are good to track motion based on pulses. They provide specific number of equally spaced pulses, but revolution are per inch or millimeter of a linear motion. And they're called optical or light encoders. They output a pulse each time only when the shaft is turned. So you have an encoder disc that will interrupt the light as the encoder shaft is rotated to produce a square wave output waveform. And so that's another application of encoders. Cutting objects to specific length. So the objects advance for a specific distance and measured by the encoder pulse determine the correct length of cutting. That's a wood cutting application. So the laser or photosensor is measuring to make sure that the distance of the material is correct. And that uses a count. We already saw the combination of timers and counters, and they're all over the place. Here's a automatic stacking program that has two conveyors that one runs perpendicular to the other one. And we have a timer on and counter of operation. Here's a motor lockout program. Using a timer, actually two timers and counters. Another, I'm just thinking right now, another application of the usage of timers and counters is for duty cycle control. Some of these counters and timers can be built into actual circuits. At other times, they'll be part of a ladder, industrial control system. But think about I want to say the case for a welding machine that is not 100% duty cycle, right? And so you want somehow to control the continuous time of work of that welding machine. Let's just say it's 50% duty cycle. And somehow you want to, either time or count the number of hours the machine has been in operation and then shut it down, right? Or automatically self-shut down. So that you don't burn or, exploit the machine beyond the duty cycle. All right, product flow rate program. There is a product flow rate program. So you have a starting switch, you have a timer, and you have a dawn bit, and you have a sensor. The idea here will be that the sensor will be on and the timer will be dawn for the counter to count 1 unit, right? Timer driving the counter produces an extremely long time delay. Again, this is daisy chaining or cascading timers, just to increase the capability of time and count operation. All right, so you might have, high-speed counting operations, HSC, and again, this is something that you can add on, or something that could be embedded into the controller itself. You have both flavors. Here is a high-speed counter in one of the Allen Bradley MicroLogic software versions. This is interesting how the word here embedded is here, because when you talk about controllers or devices within devices, the word is embedded, but maybe that was intentional, I don't know. So a typical controller has 20 kilohertz high-speed counter, which is able to count 20,000 pulses per second, right? And again, we mentioned the scan time or cycle of scan time early on, and this is somehow tied to that idea, right? You cannot count past the capacity of your controller itself. And that's why these external counters or built-in special function high-speed counters will be necessary. Okay, that was actually a pretty quick 71 slide conversation.